that we and then be continuing on to a related but distinct topic, namely that of scheduling. So I noted last time the key role that estimation plays within software projects. Estimation is a process that, as I noted, plays a role at several phases of a project. One is scoping and no-go decisions, some of which involve assessing the risk associated with to very projects. And this process of creating an honest, realistic assessment of how much resource, and particularly how much time securing some objective will involve, is a process that is therefore undertaken at the level of a few features in a given sprint of an agile process, or alternatively, at the level of a broader conception of a project, such as you have for this semester, trying to figure out, is that going to finish in time? Is it going to be something we can realistically do by the end of semester for you? For many firms, it might be by a deadline that's imposed by seasonality, like, can we get this in place for the holiday season shopping? Or could we get this in place for an event that we're supporting with the software? Maybe it's the Olympics. And if you miss that Olympic deadline, it's not much use finishing, because if your software is meant to be there to support the Olympics and it isn't done in time, you might as well just write it off, because it's not likely to be used again. So estimation is a process which takes place at several points and at different levels of granularity. And what I'm asking for your projects is that you estimate at the level of particular tasks how long they will take, and you compare that against with how long they actually take, as judged by recorded time. Okay, and at the same time, you're going to be wanting to do it not only for particular specific tasks that a person will undertake, but for the broader amount of sort of deliverables you're hoping to secure in place for the next milestone, for the next, say, ID2 or ID3. Can you achieve this in time realistically? I would expect some discussion of that within your team as to how long is this likely to take. Now, as we'll see today, for these larger amounts of time, these larger chunks of work, like the work required for a sprint of an agile process, for ID3 or ID4, or work over a number of months for a whole semester, you're going to need to consider things that get into scheduling, which is going to be a topic we're going to be diving into next in this lecture. Okay, but estimation and scheduling have some overlaps when estimation is applied at a broader level. And you'll recall that I gave some general comments on estimation. We're very poor at estimating. We tend to be poor in a certain direction. We have a strong optimistic bias. We're overly optimistic about how long it will take for us to finish things. Early estimates are used to judge project success. So rightly or wrongly, justly or unjustly, fairly or unfairly, our early guesses, if taken as estimates, turn into later judgments whether a project is successful or not. And it's a tragedy in some ways, right? Because, again, same deliverable, same amount of time, it can be viewed as a success or failure, depending on what the expectations are of the stakeholder. If they expected it 2 months earlier and were late, they may be bitterly disappointed. If they would have expected it 2 months later and were early, same deliverable, same functionality, same level of quality, they view it as a great success. So be aware that early estimates that you give can be used against you later. And that's why it's especially dangerous to have a strong optimistic bias, because you're setting yourself up for a situation where your work could be viewed unfairly just because your estimate was overly optimistic originally. And you need to resist pressure to change estimates from those who are not involved in doing the calculations needed to come up with them, and avoid letting estimates be turned into commitments. And one of the key ways that you can do this is to provide range estimates, estimates that have a small and an upper side. Now, I gave another key motivation for the use of range estimates. What is that motivation? Why use a range estimate? Why is that better than a point estimate, a single number? Why is it better for me to have two numbers?
Communicates uncertainty.
Communicates uncertainty. More than that, it forces you to think about the uncertainty. So rather than spitting out a number, which is so easy to do, and can then be used against us as the metric stick against which we're judged, you were forced to think about, okay, what's the earliest and what's the latest? It helps communicate that there's risk, there's uncertainty, and it helps that discussion starting, what can I do to help you reduce that uncertainty? To help you be more confident about this. Maybe there's certain things that can be done. Your manager gives you 2 weeks to investigate this technology you're thinking about using. Or, resolves this issue about whether someone's sticking with your project or moving to a different project or whatever. It gets the discussion going in that way, and it forces you to ask, where are the uncertainties? And this process is particularly valuable because we're very bad at considering the full set of things that can throw our schedule off. I mentioned in our closing slide from last time that there's a lot of activities that we often fall prey to this omission from our consideration. We're coming up with an estimate, and particularly if it's a point estimate, if it's one number, we often omit things from our thinking. Some of these things are things that your folks are facing, right? Illness on the part of fellow team members, that could occur. A misunderstanding with the stakeholder, that could occur. Issues having to do with someone leaving the team, that can occur very readily. The amount of time it takes to mentor a new team member who comes on board. This is one of the reasons why turnover in the team, just one of many, is so problematic. You think, well, we were 4, someone left, new person came on, we're 4 again, it's all fine. No, often there's a big loss, often extending over many months of time because you've had to bring on board this new person. Why is that? How could it be? I mean, you're 4 before, you lose someone, you gain someone. How could it be you're further behind for many months? Yeah.
Well, you're technically losing your best person because they have to go and train that new person up.
That's exactly it. Your name again?
Marcus.
Marcus, yes. Thank you. Yeah, that's exactly it. The best people are often used to train the new person. And even if that new person is trained, often they're not delivering at the level that someone who was really experienced with the project was, right? I mean, the person who left had all this knowledge about the organization of the repo, all this knowledge about the particular technologies involved, who's responsible for what, where the system's going, what the stakeholder wants, where certain documents are stored, and now you've got a new person who needs to be onboarded with that. And often there's even more processes involved in interviewing people that take time from around the team. There's loss of morale too. After all, the people who are still there when that person left have new work heaped on their plate, and that doesn't add to to the speed of the project. And now with a new person on, you can't exactly just throw it back at them because they often don't know what to do with it. So bring on board a person is often something that doesn't nearly compensate for a quite long time. And it's been estimated, I think, sometimes it's as long as 18 months. You lose someone, you bring someone on board, you could be behind for 18 months, particularly in certain specialized areas, knowing your way around. But there's other components too. Time required for cutover and deployment. For bringing, okay, so you have clients, they're using an older system, now they're gonna use your system. Think Sherbrooke, right? You're gonna use your system. It takes some time for them to bring their content from the old system to the new system. And until it's fully operational, until that's done, it's not gonna be fully operational. And that time needs to be factored in. There needs to be a time for that, a time for commissioning, a time for validation by the client, a time for installation, data conversion, etc. These are often very delicate processes. Has it ever struck you with construction? There's all this construction going on here at the UFS, right? Way over to agriculture is blocked. Construction would be a lot easier in the world if there weren't people around you have to worry about, like during the construction. You could just shut down the whole university and have at it. Things might go twice as fast sometimes. If you didn't have cars driving up and down Science Place to drive underground to the ag building, I mean, you can only imagine how much better they can make use of the space there instead of being cooped up around this new building. And it's like that with software too. We have these delicate processes where we need to go from an old way of doing things, an old system, to a new one. And that cutover is often really delicate because we can't lose time during that. It has to all be, choreographed very, very carefully. If something screws up, you're affecting a whole lot of people. They don't have the old system anymore, and they don't have the new system working. And they may be really in bad shape because of it. So these processes are, time needed to iterate with the stakeholder to clarify requirements, to deal with a misunderstanding about requirements, creation of test data or review of technical documentation by certain parties, performance tuning, etc. There's a lot of things we omit when we think about, how long will it take to write that code, to implement that feature. Even given our uncertainties there, we tend to forget about a lot of features when we give out a number. And at least if we're giving out two numbers, a worst and a best, it forces us to think through, what am I forgetting? What am I not considering? How could it be worse? What could take longer? Right? Maybe you start remembering, someone on the team is going to be taking a vacation. I remember that. Or has got to go leave on family leave for a certain amount of time. Or you start thinking in concrete terms about, this person is going for training. And it forces you to be very concrete. And much of what I'm going to be, here's another set of things, right? Yeah, training, weekends, etc. Within this sphere, much of what's required in order to really give good estimates, ladies and gentlemen, is breaking a task down into pieces. And if you talk with companies around town, this is the technique they'll often use to estimate. They'll take a plan, and instead of just giving a number for that as a whole, where you can just fool yourself, you can fool yourself totally. It's horrible. It's horrible. I'd be horrible at it. You'll be horrible at it. If you consider a giant chunk of work and say how long that will take, we pull a number out of the air, really, and it's totally disconnected often from reality, quite disconnected. But once you start thinking about the pieces of it, like what at concrete level is required, you start thinking, this has got to be in place, that's got to be in place, we have to configure this new technology, we've got to learn that technology, there may be time where we need to spread the knowledge around. Once you start thinking about the pieces, decomposition of it into small chunks, then we start to consider specifics that are more bounded. And the idea here is, with decomposition-based techniques, you identify the subpieces, and for each of them, you estimate how long it will take. And it's a really good practice, keep track of what you estimate and what it actually took. And the hope here is that over time, by seeing the discrepancy between these, we can learn to come up with better estimates, and we will have some cancellation of errors. The problem is, if we're only dealing with one number, one estimate for how long it will take, we're often fooling ourselves, and that's why I'm going to go to the range estimates here in a bit. But the idea is, it helps a lot to think about the pieces, to think about the specifics. Because if we're thinking about the general thing, forgive my language, we have no idea how long this thing is going to take. I mean, it's almost worthless sometimes to talk about how long something will take. It's going to be many, many months long. Just pull a number up like that. We flatter ourselves, but we're not very good at it. But if you're thinking about each little feature and how long that will take and what it will involve and who is needed to deliver on that and what is new is needed for the project, that we can do better. We're less likely to just conjure up some number out of nowhere. So there's two problems here, or a couple problems. One is it's too optimistic. We tend to give best case estimates, particularly if your boss is looking at you. They're looking at you. Imagine you're a newer developer and they say, how long will it take for you to implement this? Do you want to say 2 years? No, you want to impress them, right? You want to say, look, I'm pretty good, and you think, are they going to judge me by my number? It's an easy trap to fall into. So we tend to give things close to our best case. We think about the easy case, we think about the typical case, and we're not thinking hard. Client pressure, pride, boss pressure pushes towards smaller numbers. And one way to deal with this is range estimates. So you force a discussion of your uncertainty. And you can come up with these. The problem is that when we come up with range estimates, our estimates are almost always too wide. Begins with an N, ends with a W. There's two R's in the middle. Yeah, narrow. Thank you. Narrow. We saw this last time, right? The weight in metric tons of a blue whale. So one of the rules of thumb here is force yourself to think concretely. Another rule of thumb is force yourself to consider the uncertainty and communicate the uncertainty to other parties. Point estimates hide uncertainty. They hide uncertainty from the people who need to know about it often, which is the managers, right? And it requires you to think explicitly about what could go wrong if you do include those. So you actually want to explicitly give these range estimates, and you want to have optimistic and pessimistic assumptions, and explicitly distinguish these, okay? And the hope here is that over time, these start to converge. Early on, you might be quite uncertain about how long the project will take. It could go from small to large. And then over time, you're getting more and more clear about how long it will take. What's the gotcha here that I mentioned last time? As you go this way, you get clear about how long it will take. But what's the gotcha? What's the difficulty? There's not much you can do to affect it anymore, because a lot of that time has been burnt. And even if you speed up the remaining stuff hugely, there's only so much gain you can have. So we tend to become more certain at the times we can least do anything about it. Okay. So this is one suggestion authors have had. This is actually from a book by McConnell called Software Estimation, which I encourage. Incidentally, that pop quiz was drawn from that book. I think Appendix B has the answers, and maybe the quiz as well. So what he suggests is having a best case, a most likely case, and a worst case. And this is like 25% likely that it's less than that, and worst case is 75%. So in other words, it's only a 25% chance that it's higher. You can pick your numbers. Maybe it's you want 5% that it's less than the best case, 95% it's within the worst case time. In other words, 5% that it's greater than that. So you come up with range estimates. Now, the problem with these, as we said, is that typically we far underestimate the width. We give range estimates that are too narrow. We say, oh, this is a 95% estimate or a 90% estimate. Remember I asked you to do that last time? 90%. It should lie within that. And the actual numbers we got were somewhere like 30% or 40%. So they're too narrow. So we need ways of dealing with this. And past classes, some of my past years, I've gone into, in detail, a statistically grounded way for doing that. And it involves formulae, it involves specific calculations you can do and corrections to correct for the narrowness of your estimates. We don't have time to do that this year. This class is about triage. This class is about triage on your part, getting as far as you can with the limited time for client needs and the risks. This class is about triage for me because there's way too much material, and I have to figure out the 80% I don't teach. So I don't have time to do that right now, but what I will tell you is that you want to be clear about your interpretation of worst and best cases. You want to, if clients react emotionally to the width, if they say, what? So you're telling me you don't know if this will take less than 3 months, but it could take as quick as 3 weeks? Like, how can I make a decision based on that? Well, again, you use it to start a discussion. Well, one way, we could have a phase 0 where we can really shrink that estimate by allowing us to do this, do a spike prototype of this, or look into this issue, or remove this one feature that we're most uncertain about, and I'm very confident it can be done between 2 weeks and 4 weeks. Get that discussion going about where the risk is. If you don't give them the dignity of knowing your uncertainty, you can't have that discussion as readily. So be prepared. Sometimes people react. Sometimes it's off-putting. And if it's off-putting, open up the discussion about how to handle that risk constructively. Do you understand that point? Huh? Okay. People are awfully quiet. Okay. So, various people have suggested ways of doing that, and the key point here is number one, you have to correct for the width of the best and worst case. Number two, the best case for the whole project is not simply the sum of the best cases for each piece. The worst case for the whole project is not simply the sum of the worst cases for each, because it's vanishingly unlikely everything will go wrong in its worst way. So there's statistically grounded techniques that can allow you to come up with, given best and worst case estimates for the subpieces, they will allow you to come up with best and worst case estimates for the whole. Okay? I'm not going to talk about those here. I don't require that you apply them. I don't expect that you apply them, but I expect that you will know where they live, that you can access those if required. Okay? My goal today, though, is to get on to an additional topic as well. A topic closely to this, that's mapped to this closely. And that is, ladies and gentlemen, the topic of scheduling. So I'm just going to switch to this, okay? So estimation, we've been talking about, is coming up with an estimate, or better yet, estimates associated with how much time, typically, is required to secure some objective. Now we're going to talk about a trickier issue, which builds on estimation, and has to do with coordination. It has to do with scheduling, like what has to be done first. Okay, so I'm going to switch to this. We're going to go over and we'll talk about scheduling here. Okay. So estimates give us a sense of task duration and effort, but we should be cautious about using it for project length. Estimates are used sometimes for that, but really you need to do some scheduling for that. You need to consider what can be done in parallel with what. Scheduling can allow for turning many task durations into an estimate of project length. You have many estimates of the different durations of the subpart projects, you can turn into an estimate of the whole. Okay? And it turns out this can be also used to understand the flow of money and so on. So why do we schedule in the way that we'll be talking about? Well, it lowers the chance of delay, that we'll be stuck and we will not be able to deliver on time, and it assists in recovering from the delay. But it allows us, and this is really important for your projects. This is very important for the project managers out there. It allows you to prioritize tasks. You may think, what does that have to do with figuring out how long it takes? It has everything to do. Because it allows you to identify something called the critical path. Is that name familiar for you? Have you seen that in other contexts? Critical path? Maybe heard about it a little bit, but not in a classroom? Okay. The response to that is ambiguous, so I'll take that as a no. Okay? So it turns out that if you apply scheduling, even informally, often you can figure out where the critical path is. And the critical path, man, this is just like ripe for examination. Bring out the pen. Start noting. Critical path. What is the critical path? You can just imagine it as an answer. Okay? It's an answer I'm looking for in the final exam. What is the critical path? It's the set of activities, and more specifically the sequence of activities, that can't be delayed without delaying the project. It's a sequence of activities that cannot be delayed without delaying the entire project. And that implies, the corollary to that is that there are some activities that can be delayed without delaying the project. There are some activities that are less critical that they be kept on track schedule-wise. We have some leeway with them. And a technical term for it is slack. Okay? We have some give and when we schedule those activities. But the critical path activities we have to keep on, because if they slip, the whole thing slips. And it turns out that scheduling allows us to kind of monitor how we're doing based on that, if we're going to be in a bad way, and figuring out how to deal with slips, okay? With cases where things have gone wrong. And scheduling is huge in the project management field. Yeah. Mahmoud.
Actually, do you mind giving us some examples for what the critical path would be?
We're going to.
Okay.
Yeah. We're going to particular concrete cases. Okay. So with the scheduling area, there's two primary types of diagrams or depictions that are commonly used in scheduling. One of them is something called a Gantt chart. Who knows what a Gantt chart is? How many people have seen Gantt charts? Okay, what's a Gantt chart, roughly? Those who have seen them. What is a Gantt chart? What does it depict?
It shows the tasks and the timeline for each one.
Good. So it looks something like this, right? The x-axis is what?
It would be the time.
Time. And the y-axis is what?
All of the tasks.
Yeah, different tasks. And we might have one task going like this, another that can start after it goes like this, another that starts at the same time but finishes sooner, yet another that might start later, and it looks something like that. Have you folks seen that? It's hard to go into the working world much without ever seeing something like this, because it's extraordinarily common. It's called a Gantt chart, and it originated in time of the First World War in terms of planning, making plans for things that needed to happen. And it's very popular for representation of simpler schedules here. The key shortcoming of it, in its traditional form, and I'm well aware that there are variants of it that have sought to put this behind, but in its traditional form, it did not capture dependencies. What do I mean by dependency here? If this is, say, task A, B, C, and D, what are the dependencies? Yeah.
So let's say task B depends on task A to be completed.
Yeah, exactly. So task B might require task A to be completed, or at least to reach a certain point within it, for example. Maybe there's a task E here that can't be started until B is completed. So we can't start end-to-end testing until these features are in place, right? We can't start performance testing and sort of scale testing until this core algorithm is in place. Yeah.
And maybe having C done speeds up other certain tasks.
That's true. That's true. So it may be that having C done allows D and E to be done more efficiently, for example, because now there's a scripting interface in place you can use for testing or for debugging or something like that. So good point. So ladies and gentlemen, Gantt charts are very effective tools for sort of reporting where we're at, what's expected. Often we will be here at a certain time, maybe B and D are underway, and we're going to be getting E underway soon, and this is what we can expect over coming months. Very common, very powerful, very clear. But it has limited benefits when it comes to understanding how things will change if something slips. Why do I say that? Why do I say, if something changes, it's not clear, this doesn't help us a lot. So suppose, the engineering and design changed, it slipped. It slipped by a few months. Why am I saying this doesn't help a lot? Because you don't know the dependencies. You don't know what depends on that, right? Maybe the engineering design has to be done before the construction can start. And if this slips, that implies that slips. And these things slip as well. It's not clear what depends on what in their pure form, in their original form, and in most common form. So to deal with this, the standard solution is to make use of a technique known as CPM, critical path method. And this originated later, much later, than Gantt charts, almost a half century later, and it originated in a corporate sphere. And it's based on DAGs. Who knows what a DAG is? Did you get introduced to DAGs in algorithms class? What is that? Directed acyclic graph. So it's a graph where you have a set of vertices and there's directed edges between those, but there's no cycles. There's no loops back, right? You can't get stuck in a loop going around. And such a graph can be topologically sorted, meaning you can sort it so that the things, if B depends on A goes before B. And that's the idea here with the CPM diagram. Okay. The idea here is that you will use a directed acyclic graph to depict the dependencies amongst the tasks and their dependencies, And you will run an algorithm, which is a very simple algorithm. It's a very intuitive algorithm that consists of two phases, forwards and backwards, O of n time. So the runtime of it scales linearly with the number of nodes in the graph. And you will use that to figure out how long a period of time the entire project requires. Okay. So with Gantt, you might have something that looks like this. With CPM diagram, you have something that looks like this. Okay, you have a directed acyclic graph, and these are directed edges, even if they're not shown. By convention, things to the right of other things have an edge going from left to right. Okay, but it's shown here explicitly. And it turns out that there's two ways to depict this. And one is called activity on node, and other activity on arrow. By far the most common view of this these days is activity on node. In other words, the nodes of the graph, these vertices, represent tasks, activities. And the links between them, the edges, represent dependencies. Okay? So this is a fairly intuitive process that's required here to perform scheduling. Okay, we're going to perform scheduling to figure out when we can undertake tasks. When's the earliest we can undertake it, given everything else that has to be done before it, and when's the latest we can undertake it without delaying the project as a whole. Now, you may wonder, why do we need to do this? If we have a bunch of tasks, each of them we know their duration, we know how long it will take. Why is it that we have to do a scheduling algorithm to figure out how long the entire thing will take? Why can't we just add it up? Suppose we have a bunch of tasks. There's some tasks involving testing, and some tasks with development, and some tasks with documentation, and tasks associated with planning for the next deliverable, etc. Why can't we just take those tasks, we know each of their duration, we just add them up to figure out how long the whole will take? Put aside the issue of range estimates for the moment, but why can't we do that?
Lots of them can be done concurrently.
Lots of them can be done concurrently. Jeremy has it exactly on the head. They can be done in parallel with each other. So you can't just add them up, right? So someone, for example, could be engaging in a clarification of some aspects of the design while some testing is going on in other parts of the system, right? So a lot that can be done in parallel. And if you folks had to wait for each task to be done one by one in sequence, things would take vastly longer. So you can't just naively approach it like that. So why can't we just take the maximum time of any task and say that's how long the entire thing will take? So suppose we have 10 tasks and they're different lengths. Why can't we just take the maximum and say the entire project will take all of that?
One task, if it takes longer, makes another one takes less time, for example.
Okay, so that could happen, and that's an interesting case, Nick. Very interesting case. There are cases where that's true, where if a certain task takes longer, it may be that you're cleaning out issues and dealing with issues that would have delayed another task. But there's also cases where what? One task can't start before another one finishes, right? Yeah.
Well, maybe you can also break the task up into 10 smaller tasks.
Good.
But with that, maybe you just don't have 10 team members who can actually work on them in parallel if they can all work in parallel.
Good. Yeah. So that could well occur. You have only so many resources, and you can't have. In principle, you could have them all in parallel, perhaps for certain subtasks, but you can't realistically deliver on that because you don't have the people that can deliver. So we can't just assume they can all be done in parallel, amongst other things, resource constraints and dependencies. And on the other hand, we can't assume they have to be done in sequence, because we can do some in parallel, very likely. And much of your job as project managers should be in figuring out what can we do in parallel and figuring out what things do we have to watch the most, which is going to come out of this algorithm. What are the things that are going to hold the project back? What's the critical path? What's the rate limiting step or sequence of steps that have to be gotten done? Okay? So the idea here is that we're going to define the tasks. We're going to estimate the duration for each of those tasks. For each task, we're going to use an estimation method to estimate how long this takes. 4 hours, 2 hours, 6 hours, what have you. We're going to define dependencies between activities. What task depends on which? And then we're going to perform CPM scheduling. We may evaluate resource use over that. If it's acceptable, we're done. Otherwise, we may impose dependencies to capture the fact that certain resources are not available, or add resources and perform it again. I'm just going to be capturing this first bunch of steps down to performing CPM scheduling. The others require more lectures, and we don't have time to give them. I have in past versions of this class. Okay, so a key thing here is that things depend on each other, right? And another key thing is that things, in the absence of those dependencies, or within those dependencies, can be done in parallel. Okay. So I noted these days that there's activity on arrow, activity on node, but really we're going to be talking about activity on arrow. So here we're going to have tasks. There'll be a designated start task and a designated finish task, and there'll be a set of tasks which are labeled, and one task might depend on another. So the actual rigorous testing of A might have to wait until the A is finished development. The integration of A and B have to be finished till both are tested, etc. There might be some internationalization which can take place. Someone's translating our system into Chinese or translating it into French, and that can go on in parallel. The translation of the strings and the messages can go on in parallel with the basic functionality of the system being put together, and maybe there's a help system which can be put together in parallel with that. Okay, so here we have tasks on nodes. We have dependencies illustrated with the arrows. Okay, okay. So I want to communicate the CPM algorithm at its most basic. And I may ask you, in fact, there's a high likelihood I may ask you on the final exam to undertake a CPM example. So it's worth paying attention here. So the CPM algorithm, I need you to know what it requires, what it gives us, what it outputs, and I need you to know basically how it works in terms of the two passes that are involved. What does it compute on each pass? Okay? So the input to it is quite simple. It's an identification of the tasks, such as their name, their durations, and their dependencies on one another. The output for the CPM, please get this right. Oh, you don't know, it hurts. It hurts. It hurts to see students who leave this unanswered, unable to answer it. It's not a hard question. It's not a hard question. At least be able to answer it, please. Input, output. Okay, the output, it derives early start for now. What is the mark my words, what this means, not just the name. Early start. So it's good to know the name too, because many times they can't even give the name. Yes, early start. What is the earliest time that this task can start, given everything that has to go before it, that has to be done before it? Given its dependencies on other tasks, right? Given the fact that this overall end-to-end testing depends on this integration of the help system, internationalization, and these different components. When's the earliest this can start, given everything that has to be done before? Do you see that? Okay. So ladies and gentlemen, CBM algorithm for each task gives an early start. The earliest it can start given everything that has to be done before it. The latest it can start, mark my words, man. The latest it can start without delaying the whole project. The difference between those is something called slack. Float. It's how much give we have for that task. It can't start before this time, and it needs to start by this time to not delay the whole project. And the difference is float. The difference is slack. The algorithm also gives us the earliest a node can finish, given the things that have to go before it, and the latest it can finish without delaying the whole project. But those are important to know about. But in this simple version of it that we're dealing with, they're just the early start and early finish plus the duration of the node. How long? Yeah.
If we're to put it in a diagram, how do we specify the differences between the
Early
start
start.
and late start?
I'll show you on the board. Not 5 minutes hence, okay? Okay. Thank you for that question. So I'll be showing a notation, and I would ask you in the exam to use the same notation, okay? In other words, I will tell you the notation. I'll remind you of the notation there, but you'll see how it can be used. Okay, this is an algorithm that is linear in the task count. It scales as theta of n. It runs in time linear to the number of tasks. And it involves two passes to compute these two things. The first pass, the forward pass, computes the early start and early finish. The second pass computes the late start and late finish. Okay? The forward pass, the first pass, early start and early finish. The backwards pass, the second pass, late start and late finish. Okay? Okay. So there's going to be two passes of this algorithm. Okay? In the first one, you're going to be setting the early start for each node, and the early finish is just the early start plus the duration. If this task can't start before day 3, and it's going to take 2 days, it can't finish before day 5. The earliest it can finish is by day 5. If it takes 2 days, it can't start before day 3. It can't finish before day 5. Do you appreciate that? Okay. The backwards pass is going to compute how much time the whole project would take, and then it's going to compute successively backward for there. The latest a given activity can finish without delaying that whole project, the whole thing, and then the latest that it can start without delaying the whole thing. Okay? Okay, now the notions for these are very straightforward. This is common intuition. Okay, it's 8 a.m. Suppose you want to know what's the earliest time you can arrange. So it's 8 a.m. on a Saturday morning. The alarm goes off. What's the earliest time? So some of your teammates want to meet with you about 371 project at Spain. What's the earliest time you can arrange to meet the team after performing some tasks? Okay, so you can take a shower. You boil water in a water heater for breakfast. You can eat breakfast. You can walk to campus. What's the earliest time you can meet your team?
Probably about 8:55, because you have to take into consideration where you're walking on campus as well.
Okay. So that's good. And the 8:55 came from. Okay, so this is walking to campus. So where did the 8:55 come from? So that's 55 minutes from now. And where did the 55 come from?
Well, I'm assuming that they don't want to boil water and take a shower concurrently, so I added 15.
Okay, good. Good. So that would be the consideration. Suppose you can safely, it's in a water heater. Suppose you can have that on while you're in the shower. Someone else is in the kitchen. You don't have to watch it. Then you can do these in parallel, right? So in total, it'll be 10 minutes before breakfast is ready. Meanwhile, you could take your shower, and then you can eat breakfast, right? And that will be done 25 minutes from now. And then you can walk in, and then 20 minutes after starting that walk, that is 45 minutes from now, you could meet up, right? If these could be done in parallel. If these can't be done in parallel, you see how it drags out further. Do you see that? So this is common reasoning, right? We're thinking, okay, while I'm waiting for the taxi, I can do this. So I don't have to do that after, after that task. Okay, so that's the intuition between the forward pass. And the key idea here is, ladies and gentlemen, if there's two tasks, like taking a shower and boiling water, that can be done in parallel, you need to consider, is it the max or the min of their times? It's the... So suppose I can take a shower and boil water. I can be done with both based on time. Is it the max of the two times of the subtasks or the min?
Max.
The max. Because, I have to wait until the last of them finishes, right? Okay, so it's the max of the times here. Okay, now suppose your plane leaves at 12 p.m. It leaves at noon, okay? You want to know what time you have to get up to make the plane, okay? So you have a plane leaving from the Saskatoon airport at 12 p.m. So you want to take a shower. You have to boil the water in that water heater, that safe water heater, right? You want to eat breakfast. You want to call and wait for a cab. You have to take a cab to the airport. You have to check in. You want to sit at the gate to be comfortable at least 40 minutes, and then sit on the plane before takeoff. The plane leaves the gate at 12 p.m. What time do you have to set the alarm for? How would you figure that out? I'm not going to ask you to do it in the head, but how would you figure it out?
I work backwards.
You work backwards, and that's the backwards pass. That's what's called the backwards pass. You sort of are going backwards, right? Okay, so 12 p.m. the plane leaves the gate. So you need to be on the plane 20 minutes before that, right? And you need to go back another 40 minutes for when you arrive at the gate, and another 10 minutes, another 20 for the cab. Now, you can. Where's the opportunity for parallelism here? What can be done in parallel?
While you wait for the cab.
Yeah, while you wait for the cab, you could be eating breakfast, right? And boiling, and you could do some of these in parallel, take a shower and boiling water at the same time. So here you're reasoning through, what's needed. Now here the reasoning is a little bit different, because if you have to be, for example, eating breakfast by a certain amount of time for you to catch the plane, and you have to call and wait for the cab by a certain amount of time, you're going to need to take the minimum of the latest times you could start those without missing the plane, in order to get the time you have to start either of them. Okay, so there's actually a minimum here. I need to get up at the minimum time that's associated with the time that I need to, the earliest time I need to start any project to get on there. So in other words, if taking a shower, I need to get in the shower by a certain time in order to make the plane, and I need to start eating breakfast by a certain time, I need to take the minimum of those to catch the airplane. Okay, it's I need to be able to leave for the airplane, or start getting ready at a time that will be sufficiently early to allow me to undertake all the tasks. So it has to be by the time that's the minimum of the task there. Do you appreciate that issue? So working backwards is all great while it's in sequence, but then once it comes to things that can be done in parallel, you're going to be saying, okay, these can be done in parallel. Well, we need to start them by the earlier of the times any of them have to be started to make that plane in time. Okay? we'll see this. So this is a two-phase algorithm. So I'm going to take an example here, and we'll do it on the board. Okay, and this is the notation, Peggy, that I was talking about. Okay, this is the notation, and I've been favoring this side of the board. So out of equity, I'll favor this side. Okay, how you doing? Good to see you. Okay, so we're going to put this on the board because I can't, in a good way, write on the screen. And we're going to use this notation with sort of hexagons of sorts. The top number here is going to be just the task number, and the bottom number is going to be duration. Okay? So I have taken a bunch of tasks, and I've boiled it down to a DAG, to a directed acyclic graph. I've taken these tasks, like requirement solicitation, and I put it into here. And task number 2 is design, and put it into here. Do you see that? Do you see that? Okay. So what I'm doing here is putting this onto the board. Just copying it here. So this is task 2, and it's 7. And maybe you can just read these out to me to speed the process. So this is task 3, and what's the amount of time? 2, thank you. And then we've got a series of 2 more along this sort of backbone.
4 is 2.
Okay, so this is 4, and it's 2, and the next one?
7 and 6.
7 and 6, good. Now, this is not a purely sequential graph, because we have a branch off at 7, and this guy down here, that gal, what's the number? Number 5, and it takes 4 days. And there's another one here, I think, and it's what? 6 and 4. And then this one needs to be finished. Both of these need to be finished, numbers 4 and number 6, before we can. Mumble. 4 and 7 before we can finish the entire thing. Okay? Are we okay with that? So just transcribe that. Now, what I'm going to do, and this relates to Peggy's question before, is just note that when we write this in this notation, this is the task number here. This is the duration. And then we write up here early start. Okay? I'll just write ES, early start, early finish, and then late start, late finish. Let me emphasize again. What does early start mean? Earliest we could start this activity given everything else that has to be done before. Everything else it depends on. Early finish? The earliest we could finish the activity given everything it depends on. How about late finish? The latest we can finish this activity without delaying the whole project. And late start, the latest we could start the activity without delaying the whole project. Okay? So the earliest, this is all about, given everything that has to be done before, what's the earliest we can possibly start? Latest, when do we have to finish these so we can make our plane at 12? Okay. Forward, backward. Right? Okay. Okay, so we're going to go through and we're going to schedule this. Now the basic deal here is we're going to, for the forward pass, we're going to be computing the early start and early finish. And it's going to be delightful ease while we're in a sequential situation. But it's going to get more involved when we have things that have to depend on multiple predecessors, okay? So watch this, okay? So I'm going to start at day 0. The earliest that number 1 can start is what then? 0. And what's the earliest it can finish? Day 2. Good. Okay. How about this guy here, number 2? What's the earliest he can finish? Given that it depends on 1, that 1 has to be finished before 2 can start. What's the earliest he can start? 2. And when's the earliest you could finish? 9. Okay. Okay, number 3. What's the earliest she can start? 9. What's the earliest you can finish? 11. Okay. This one here, number 4. What's the earliest it can start? 11. Earliest it can finish? 13. Okay. So task 7. Earliest it could start? Okay, 13.
Yeah.
13. And the earliest it could finish? 19. Okay, good. So that's the top here. Now we're going to continue on the bottom. What's the earliest number 5 can start? 9. Yeah. Why is that? It's because it depends on 2, and the earliest 2 can finish is 9. So this can start as 9. Do you appreciate that? I'm not saying do you like it, but are you okay with that? Do you? Okay. Hearing no objections, I'll move on. Okay. And the earliest this can finish is 13. Where did I get the 13? Yeah, 9 plus 4, right? Do you see that? I mean, if this can't start before 9, there's no way we can finish before 9, given that it takes 4 months, right? 4 days, yeah? Okay. Number 6, what's the earliest it could start? 13, given that it depends on 5, right? I'll put in these things, okay? Great. And what's the earliest it could finish? Okay, now, this is where the max comes in. Remember I was saying before? You have to be considering the max of any time. Like, you're going to be in the shower, you're going to be boiling water. When is the earliest time you can finish both of those? It's a max of those, yeah? Those early starts. So what's the earliest time the entire project could finish? 19. Why 19? Where does that come from? Whence does that come? This guy, right? I'll give you a hint. This is the critical path, ladies and gentlemen. This is the path that can't be delayed without delaying the whole project. Do you see that? This path we're going to actually have a bit of float on. Okay, so the earliest that this could finish is 19. Okay, now we're going to do the backwards paths. Okay, now here, so in the forward path, the thing we have to watch out for is when we're going forward and things came together. And it's the same thing with the backwards paths, except we're going to be seeing where they come together, so going backwards, or split if we were viewing it from the start, okay? So, 19. Okay, so let's do the top one, because it's easy. When's the earliest, or sorry, when's the latest node 7 could finish without delaying the whole project? 19. If we delay it, the whole thing's delayed. Do you understand that point? When's the earliest we could, or when is the latest time we could start it without delaying the whole project? 13. The whole critical path, it's going to be that. Do you see that? I mean, I could just work back. Each one of them, okay, just to be clear where this came in, the latest this could start, number 7 could start without delaying the whole project is 13, right? That's 19 minus 6, yeah? And the latest that number 4 could finish, given without delaying the whole project, is 13, right? If it's delayed by that, then this guy's delayed. And that leads to, do you understand that? Yeah, okay. So this is 11, and it's just delightful, right? Until we're gonna hit here. And then we have some figuring to do. So let's deal with the lower side. What's the latest that we could finish number 6 without delaying the project? 19. What's the latest we could start it without delaying the project? 15. How about for this guy here, number 5? 15 and 11. Okay, so ladies and gentlemen, this lower path, we have some give. We have some slack. We actually could delay, without delaying the whole project, we could delay number 5 by how many days? 2 days. We could do it by 2 days. And then it would start at 13. It would go to 17. This would start, excuse me. Yes, that's correct. So we could start at 13, right? Okay, so what's going on here? Hold up for a second. So this is 4, yes, that's correct. No, this is incorrect. That's not 15. Yes, it is. 15, 15, and this is, yes, okay. Don't know where I'm at today. Okay, so ladies and gentlemen, this lower path has some give. It has 2 days worth of give. Do you see that? There's 2 days difference between these guys, or equally much so 2 days with the late finish. You see that? Yeah. Okay. Now let's finish this though. When's the earliest, ladies and gentlemen, that node 2 could finish without delaying the whole project? No, sorry, the latest it could finish without delaying the whole project. Sorry. What? Yeah, it's 9. Because if it goes later than 9, what's going to happen? It's going to delay this whole upper path. Would this guy be able to tolerate it?
Yeah.
If it goes later than 9? Yeah, it would. Be able to tolerate up to 11. But 9. Okay. And so the latest we could start it without delaying the whole path? 2. And this guy here, first guy, number 1, 2, and 0, right? So ladies and gentlemen, the critical path here is this one here. This is the guy that has 0 float. Each of these nodes, when you talk about the float of a node, it's the difference between the early start and late start. It's the difference between when we can possibly start it, given everything that goes before, and the latest we could start it without delaying it. If those are the same, we have to start it at the earliest possible time that we can. Do you understand that? On the other hand, if those are different, we have some leeway. Without delaying the project, we could start it later than the earliest we possibly can. Do you understand that point? So that, ladies and gentlemen, is the critical path. This is a non-critical path. And what we had to do here, you'll notice, we ended up taking the minimum of 9 and 11. Why? Why minimum? Because we're considering the latest we could finish this thing without delaying the whole project, right? And if there's even one successor of ours, one thing that this goes to, which has to finish earlier, this node has to finish earlier. Do you understand that point? If there's any other node that depends on like number 2 being done by time 3, then this, to avoid delaying the project, then number 2 has to be done by time 3, right? Do you understand that point? So going backward, when we have this kind of split, and we see it at node 2, we have to take the minimum of the times, because we have to finish that node by the earliest of the times that are needed by our successors to avoid delaying the project. Do you understand that? It's like we have the strictest constraint in place. Meanwhile, going forward, the forward pass, we're taking the maximum of these two, right? Here, because we're asking, when's the earliest we could possibly finish it? And if even one of these goes late, we have to take the maximum. Do you understand that point? So, forward pass, max, where you encounter this kind of coming together, and backwards pass, where you encounter this split, working backwards, you have to take the minimum of the time by which it could be secured, okay? I want you to know the float, the difference between early start time and late start time, and be able to take that into account in your calculations. So scheduling, ladies and gentlemen, is one of the most basic tasks that's undertaken for project management out there. And what I expect you to be able to do for your projects is to tell me where the critical path is for a given project. Do I expect you to show me a fully defined CPM diagram? I don't require that. Some teams have done that. It's not a bad exercise to think through roughly what that diagram would be. But I'd at least like to be asking, where is the path that if we're thinking about the next deliverable, we cannot slip? We have to be hitting this, one-on-one, because that's the path on which you as project managers need to focus, and the dev leads and test leads. Because if you slip that path, you're not going to hit your deadline. And there may be other tasks that have leeway associated with them. They don't have to be completed just on time because they're going to be waiting for other things, right? This lower path, this guy was waiting for this guy to complete, right? That's why there's this difference here, right? He can finish by time 17. So he's gonna, if he finishes by time 17, he's gonna be waiting for number 7 to complete. Do you understand that? So there's gonna be some tasks like that for your projects where, yeah, it'd be nice to complete it early, but it doesn't gain us anything because we're gonna be waiting for the UI to be done, or we're gonna be waiting for this aspect of the requirements to be firmly in place or whatever. And there's going to be other tasks where we cannot let this up. We got to meet with the stakeholder, that week, or we're going to be in a bad way. Do you understand that? So being clear about critical path versus non-critical is critical. Okay? That's all we have time for today. Thank you very much. And have a wonderful break, and I'm looking forward to reviewing ID 2.
Just a really quick question. For estimating the CPM, is it targeted for